Right now, we're going to take the concept of momentum a little bit of a step further and talk about impulse. Impulse, we are going to define as the change in momentum experienced by an object. Remember, as we've talked about impulse for the last couple of days, momentum for the last couple of days, it's always been the momentum at a particular time. Here's the mass, here's the velocity, what's the momentum right now? Or the object falls, what's the momentum at the end of the trip, after the fall? But not during the fall, not over the time interval. When we talk about the momentum changing over a time interval, we're going to talk about this concept of impulse, the change in momentum. Now, there's a couple of things that are required for an object to have momentum. We know that, right? It's mass and velocity. We talked about that on Thursday. We also talked about that in our review today. Momentum and velocity, mass and velocity, both required to have momentum. But there are also two different things that are required to change an object's momentum. What do you need to do to something to change its momentum? In other words, what do you need to do to something in order to make it go faster or go slower, which is really what you're going to do to change its momentum, right? Make it go faster or slower. What can you do to make it go faster or slower? You got to apply a force. So the first thing that's required to have an impulse, a change in momentum, is a force. If you don't push on something or you don't pull on something, you're not going to change its velocity. Now, intuitively, you know that if you push for longer, you're going to change its velocity by more. If you push for a shorter period of time, you're going to change its momentum by less. What else affects the amount of impulse or the change in momentum besides the force? The time. So we've got two things that affect momentum, it's m and v. Two things that affect the impulse, it's f and t. Impulse is a vector quantity, namely because it's the change in momentum, and momentum is a vector. But if you look at what it depends upon, force and time, well, it depends upon a vector. It depends upon force. So, of course, any way you look at it, impulse is going to be a vector quantity. Now, what's the equation that we use for impulse? We're going to derive this one, actually. I'm going to show you where this one comes from. It comes from Newton's second law. You guys remember what Newton's second law looked like in Physics 20? First law was an object in motion stays in motion, blah, blah, blah. Okay, third one was object A applies a force on object B, B applies an equal and opposite force on object A. Max, do you remember what the second one was? No? The acceleration is directly proportional to the force and inversely proportional to the mass. In other words, F equals ma. Remember that? Does that ring a bell? It better. Okay. Maybe not necessarily as Newton's second law, but you better remember this equation. F is equal to m times a. Now, what I'm going to do here is replace a with delta v over delta t. Is that okay to do? Yeah, acceleration is change in velocity over change in time. So if I wanted to replace a with delta v over delta t, I can. Now I'm going to rearrange this a little bit. I'm going to take the t up by multiplying. It becomes f times t equals m times delta v. So far, so good? What's the equation for momentum again? M times v, right? M times v. Is this momentum right here, m times delta v? No, it is not. M times v is momentum. M times change in v would be the change in momentum, right? What's the change in momentum defined as? Impulse. So m times delta v is impulse. It's delta p. But if m times delta v is impulse, then f times delta t must be impulse as well. Perfect. That takes us back to what you guys told me just 2 minutes ago. Two things that affect impulse or change momentum, force and time. Everybody take a look at your data sheet right now. On your data sheet, you will not see this equation written exactly the way that you see it written up on the board right now. F times T equals M times delta V equals delta P. On your data sheet, under momentum and energy, bottom left-hand corner, you see F times delta T equals M times delta V. You see this. Each of those terms is equal to impulse. F times T is equal to impulse, the change in momentum, and of course it is. Bigger the force, bigger the time, bigger the change in momentum. But M times delta V is also equal to impulse. Mass times however much the velocity changes is also equal to impulse. Yeah, Travis? Okay, I'll get you one. Now, clearly we're going to use this equation to solve some problems, but what problems are we going to solve using this equation? If a question says impulse, calculate the impulse, then, I mean, it doesn't take a rocket scientist to figure out that we're going to use impulse when this question says how much impulse is blah, blah, blah. But there's more subtle questions, more subtle situations in which we're going to use that equation as well. Okay, if you see the words change in momentum, or momentum gained, or momentum lost, then we're going to use impulse. You may use a part of the impulse equation that does not appear on your data sheet. You may say delta P is equal to F times T, or you may say delta P is equal to M times delta V, but you're going to use impulse. And secondly, and this is the really useful place, or this is the place where impulse is a really useful concept, is when we see a force and a time in the same question. The question may not even mention the word impulse. It may not even mention the word momentum. The question may seemingly have nothing to do with momentum or impulse. But if I see a force and a time in the same question, then we know the momentum has to have changed. You can't have a force acting on something over a certain time without changing the momentum. There has to be an impulse. And if there is, then let's use that concept to solve the problem. Let's take a look at one example here now. 9.3 on 458, it says, to improve the safety of motorists, modern cars are built so the front end crumples upon impact. A 1,200 kilogram car is traveling at a constant velocity. It hits an immovable wall, comes to a complete stop in 0.25 seconds. My brother was in the 1980s, when he was in grade 12, when he was your age, was driving my parents' brand new car at 93 kilometers per hour. We know that it was 93 kilometers per hour because that's where the speedometer stuck. It literally stuck there. As he comes around this corner on the highway, nodded off, and ran into, head-on, ran into the concrete abutment for an overpass. Okay, that was pretty immovable, that object. The car came to a stop. I don't know how long it took to come to a stop, but it was pretty quick, right? He survived, mainly because he was wearing a seatbelt and because the crumple zones in the car. Okay, if the car didn't have crumple zones, there is no way that he would have survived that collision. What do crumple zones do? Now, you'll see in a few minutes here, okay? What's the impulse provided to the car? Okay, clearly this car is slowing down. It's stopping. It's changing its momentum. It receives an impulse. Okay, we want to find the average force exerted on the car. And then question C, that's kind of a separate question. We'll look at that in a minute here. Okay, here's my mass. Here's my VI. My VF is going to be 0 because it comes to a stop. Here's my time. I want to find the impulse, and I want to find the force. Clearly an impulse question because it says what's the impulse. Impulse is equal to F times T, but it's also equal to M times delta V. Which one do you want to use, F times T or M times delta V? M times delta V. Now is when we look at our givens, right? We're trying to look at the bigger picture, but there comes a point when once we know what's going on, we've got to look at our givens to see exactly which equation we use. M times delta V. The mass is 1,200 kilograms. Delta V is 0 minus 8. Right, final velocity minus initial velocity. That gives me 9.6 times 10 to the 3 kilograms meters per second. Actually, it's going to be a negative 9.6. Where's the negative come into play there? Travis? I'm sorry? 0 minus 8, yeah. But what does it mean? Well, the impulse is to the left, but you can also think of it as a loss of momentum because it's a negative impulse. Question B, what's the average force exerted on the car? Well, now let's use the other part of the impulse equation. We've got negative 9.6 times 10 to the 3 divided by a time interval of 0.25 seconds here. Do that math. Negative 3.84 times 10 to the 4. Is that right? Good? It's a big force, right? That's a big force. Let's take a look at C now. For the same impulse, and remember, this car, no matter how long it takes this car to stop, is going to experience the same impulse. When we calculated the impulse up here, we didn't pay any attention to whether it hit a concrete wall or whether it came to a slow, gradual stop at a stop sign. The car was moving this speed, now it stopped. The impulse was going to be the same no matter what, no matter how it stopped. Question C, it's got the same impulse, but it stops differently so that the time of impact is 0.04 instead of 0.25. In other words, it stops a lot quicker. What's the force going to be? We're going to say force is equal to delta P over T. Delta P is negative 9.6 times 10 to the 3 newtons, kilograms meters per second, divided by a time of 0.040 seconds. We get negative 2.4 times 10 to the 5 newtons. That number is almost 10 times bigger. Hold on one second. That number is almost 10 times bigger than the force we got in question B. Why? Because we stopped quicker. What did it say in the beginning of the question, the stem of the question here? It says crumple zones are safety features. Crumple zones make it take the car longer to stop. The car stops over a bigger period of time when you have a crumple zone than if you have a smaller period of time. What does that do? Increase the time, decrease the force. It's not impulse that hurts you. It's force that hurts you. You want to decrease the force, not decrease the impulse. Hey, that's it for today, guys.